So, then, welcome. Let me just see whether, yes. Oops, that was the wrong button. Sorry for this. Mach bitte die Tür zu. Okay, sorry for this strange start. Yeah, welcome to the, what is it, the 9th lecture in Introduction to Lattice Boltzmann. Today we are talking about the multiple relaxation time method in 3D. So last time we talked about this in 2D, and I told you that here we have many more ghost moments that we have to deal with, and that the orthogonality of this will cause some problem. Okay, the original work for multiple relaxation time lattice Boltzmann methods in 3 dimensions is from de Humier et al. In the Philosophical Transactions of the Royal Society in 2002. And in this, they had, of course, they had as this was this time, they used unweighted orthogonal MRT methods on the D3Q19 and D3Q15 lattices. So you notice there is no, there was no D3Q27 lattice used then, and we will discover today why this was not possible. Okay, now about this paper. This paper has, I think, 3,000 citations or something. Yeah, so it has a lot of historical relevance. This is good. What is not so good is the actual correctness of all of this. And okay, maybe I'm not using exactly the right word, but with correctness, I don't mean that they have a lot of typos and the equations are not, I mean that they have mistakes in their equations. That's not the case. With correctness, I mean the entire concept of the unweighted orthogonality that in this paper was not justified, and then they give specific sets of relaxation rates that they don't actually derive, but they give them, and with these relaxation rates, yeah, which are very special, it kind of works under some circumstances, but not. This is not very general. Okay, and therefore, today we talk about what is seldom said about these things. So the next chapter is what nobody told you about multiple relaxation times. Okay, let's use as a starting point the tensor product lattice. Like the tensor product lattice, I remind you, is the one that we start from the with in one dimension where we have a particle going left, particle going right, and particle staying where it is. Yeah. So and then we multiply this in the the additional dimensions, and of course this gives rise to the D2Q9 in 2 dimensions and to the D3Q3 by the power of 3, so D3Q27 lattice. And now the challenge is that we wanted to derive a method with multiple relaxation times. So we need to know how many moments there are to see how many different relaxation rates we could choose. Yeah. So question: how many independent relaxation times can be imposed? And this, of course, under the assumption of isotropy. Does anybody remember how many relaxation times we had in 2D?
Four.
Okay, we had one for the hydrodynamic, we had one for the pressure, then we had one for the third, and then one for the fourth, right? This is 4 relaxation rates. Yeah. So you already see that due to isotropy, we have two third order. So they need to have the same rate, right? And now let's look at, I mean, you could have a guess, but I think we'll have to figure this out by using the grouping of the moments. So first of all, we have to determine, okay, we use raw moments here, raw countable moments. And first we have to determine which they are. So of course we have M00, M100, M010, and M001. Yeah, so these are obviously the conserved guys. So there is no relaxation. No relaxation to these. Then we have hydrodynamic guys, for example, the one M110, yeah? So this is one where in 2 dimensions we have only one of these, but because we have only 2 indices, but now we can permutate these 3 indices, obviously 3 times. So because there will be an M101 and an M011. So this is 3 permutations. Then we have the M200, but from them we remember that we had to group them according to the pressure and the part that is not the pressure. The part that is not the pressure was in 2 dimensions M20 and M02. And now we have them again, just we have one index more. And this, of course, now has permutations, namely M200 minus M002. And by the way, this is a thing that now confuses a lot of beginners and confused me also when I was a beginner to this, because there is, of course, another permutation to this, namely what would be the other? So, for example, M020 minus M002, right? So why is it not a good idea to add this here? Two reasons. Any idea? Okay, think about 2 dimensions. In 2 dimensions, we have M0, M20 and M02. So we have 2 of these moments, yeah? And we can, so we have to regroup them as their sum and their difference, right? Now, in 3 dimensions, we have 3 of them, and we can generate here, for example, 3 different permutations of this moment. But if we generate of the differences, right? So if we take these 3 different, these 3 differences, we have mapped 3 to 3. So there is no additional information in having the sum of all 3 of them. Yeah. Also, this would not be independent because you can combine these 2 to generate the other permutation. So for what would you do? Yeah, you would add, for example, the first one minus the second one, yeah, would give you M002 minus M020. Yeah? You know what I mean? No reaction. Yes, okay. Let's say, so these are the hydrodynamic moments. The hydrodynamic moments that relax, whatever, the relaxation rate of them is omega is the same as in BGK. So these guys are fixed. And then we have the one that gives us the pressure. Now, because we are in 3 dimensions, this has 3 parts here, 0, 2. So, and this is the acoustic moment. And this is where we apply omega pressure, which will adjust the bulk viscosity. And this is a thing that disappears in acoustic in diffusive scaling. Okay, so these are the things that we have to take care of first, and then there is a list of ghosts. And now, because we are in 3 dimensions, we have more ghosts. So in 2 dimensions, we had 3 ghosts. 2 of them were third order moments, and 1 of them were fourth order moments. Here again, we have, of course, third order moments. So I'll name this group now 3, and there are 2 different types of third order moments, namely the group A, 3A, is M102, which has how many permutations? Give me a number.
3.
3. Is everybody in favor for 3?
2.
I would have said 3 too.
Yeah. Okay, but because now you are 2 guys saying 3, maybe then this means it is 6. Okay, why
That's
you know, the guy up here, when we talk about this here, yeah, you exchange 1 and 1, you get the same permutation, right?
Yeah.
Yeah, but here you have to exchange 2 and 1 and also 0.
So we get 6.
Yeah, so we'll get 6 permutations of this. 6 permutations. And then there is a single other one. This is group. This is 1, 1, 1. You see, this has only one permutation. So, okay, we have 7 third order moments. Yeah, in 2 dimensions we have 2. Yeah, so right, yeah, this makes sense. If in 2 dimensions there are 2 of them, then in 3 dimensions there should be 3 of them, but there are 7. Okay, you see, it's getting more complicated with the ghosts. So then we come to the fourth order, guys. So 4 order, there's also different groups, namely M220, which has how many permutations? Very simple.
3.
3, yes. So then we have, right, M211. Yeah, so the same thing. There is one repeating index, so it means it has 3 permutations. So this is B. And then there is the 5th order, guys. So the 5th order, guys, is M221. Obviously, this has again 3 permutations. We love the number 3. And then there is 1/6 order guy, M222. Of course, no permutations. So, question. Has each type its own relaxation rate? Okay. Why is this a complicated question? The thing is, even though these moments are not arbitrary, we made them countable. From their physical meaning perspective, this grouping is a bit arbitrary. And I remind you that in the other moments, for example, M200, M020, and M002, so they are all one group or one type, yeah? They are one type of moments, but they come with 2 different rates. So this is because of isotropy. And the thing here is this M200 plus M020 plus M002. This is isotropic. And isotropic means it is invariant under rotation of the coordinate system. Okay, we have to look for invariances in rotation. So let's look at rotation of moments. Okay, for this, I mean, we are in this rotation about what? Yeah, so our lattice is a distribution in velocity space. Yeah, so we look at our lattice velocity of the population that we call Fijk. Yeah, and this has the velocity xi is the vector I, j, k times delta x by delta t, which is the lattice speeds. So we can write this as I times the unit vector in x direction plus j times the unit vector in y direction plus k times the unit vector in z direction, and formally we have to multiply all of this with delta x by delta t so that we get a velocity. So, and the rotation now can be written or specified through a matrix. So let's say we are looking at a vector I, R, J, R, K, R that is a rotated matrix. Yeah, so this can be specified as I times a rotation matrix R times the first vector plus J times rotation vector matrix times the unit vector in y direction plus k times rotation vector. Why do I always say rotation vector? Rotation matrix in on the unit vector of z. Yeah, so this will turn ijk into ir, jr, and kr. So now I hope you're familiar with rotation matrices. So there's some special rotation or specific rotations that you can look up in, I guess, Wikipedia. So the rotations about the different axes, meaning x, y, and z axis. Okay, I hope you are familiar with them. So there will be a matrix for rotation about the x-axis. This is 1, 0, 0, 0 cosine. Okay, we'll call our vector alpha, our angle alpha minus sine alpha 0 sine alpha cosine alpha. Write this a bit different, like this. So there will be r rotation about the r-axis being the y-axis. Oh my god, I need some holidays. So this basically looks almost the same, just a permutation of this. Sine alpha 0 cosine alpha. And lastly, we have this about the z-axis. Z is cosine alpha minus sine alpha 0 sine alpha cosine alpha 0 0 0 1. So these are reminder for these rotations. Okay, so then very simple. If we rotate about the x-axis, then I will call this vector, so the indices I with the indices x, I, j, k with the indices x, I'll call this a rotation about the x-axis. So this is the rotation matrix about x, ex plus j r x y plus k r x z. So okay, with this I mean if we take I, j, and k and rotate them with the rx, then I'll call this the indices ix, jx, and kx. So the reason why the acoustic mode is set to be, the acoustic moment is said to be isotropic, is that we define this moment MP as the sum to 0, 0 plus M02 plus M002, yeah, which is, according to our definition, the sum over ijk from -1 to 1 over I square j square plus k square into Fijk. So, and this thing here, as you could potentially tell by just looking at it, gives you the length of a vector square. Yeah, so I mean, it almost looks like the what is it? Not the Cartesian, the Euclidean norm is just is just the square, is just the square of it. So we don't take the root. Yeah, which means it's just the length of the vector without any direction. Which means that the rotation of this with any rotation matrix, with any legal rotation matrix to another coordinate system, will always yield the same thing. So say we have IR rotated by any given matrix R without any specification, then this will be the same as the original. Yeah, so if the indices, if the sum of these indices, this kernel function is the same in each coordinate system, yeah, so then the moment will also be the same in all coordinate systems. Yeah? And therefore it's therefore MP is invariant under rotation. Okay, let's look at our hydrodynamic moments as an example. Hydrodynamic. So we specifically now look at M20 minus M020. So which we get from the sum IKJ starting from -1 to 1. Yeah, I square minus J square. Fijk. Now let's see. Okay, so this is a moment that is biased. So this is in the xy plane, right? It's in the xy plane, and obviously the z vector is orthogonal to the xy plane. So if we want to rotate this in plane, we would rotate it about the z axis. Axis or axis, I don't know. Just so the indices rotated about z give us, so if we do the multiplication of the unit of the unit vector with the matrix, yeah, which I don't do in all the detail now, just write the results. Hopefully they are correct in my paper. J minus sine alpha cosine alpha. So this is a simple multiplication of, sorry for this, of this matrix with the unit vector. So we'll get first this, then this, and then this vector here. And the last one here is, of course, K001. So from this, we can determine what is I set square. Yeah, so this is obviously, we get here we get I times the cosine of alpha plus j plus, no, not plus, obviously not plus. So here's a minus j sine alpha, and there's a 0, so nothing else. So we get this square, and what we have to do is to take the, what is this, expand it. So we have I square cosine alpha square minus 2ij cosine alpha sine alpha plus j square sine square alpha. Yeah. And j z square is, so what we have here is I times sine alpha. Here we have plus j cosine alpha, and we have to take this square, so we'll end up with I square sine square alpha plus 2ij sine alpha cosine alpha plus j square cosine alpha square. Okay, everybody agrees? So please look whether I missed some square or something, yeah? Okay, now what we want to know is, how is this kernel that we use to compute this hydrodynamic moment, how does this look in a different coordinate system? So the kernel is I square minus j square. So in the rotated coordinate system is I z square minus j z square. Yeah, so what we are going to do is we isolate I square, and see, we got this together with the cosine square alpha. This is what we have up here. Minus, because there's a minus here, minus sine square alpha. Then we got minus 4 times, because we have minus 2, and we have minus plus minus 2. We minus plus 2. Okay, so this gives altogether 4. Sine alpha cosine alpha plus j square sine square alpha plus, no, not plus, minus. Sorry, because we have a minus here, so this is cosine square alpha. Okay, so this can be rearranged by recognizing that we can put these two guys together, recognizing that they have the opposite sign. So we'll have I square minus j square times cosine 2 alpha. So we, you know, we use this, what are they called? Well, the relations of sine and cosine, yeah, that we can to the simplification for this, yeah, for ij sine alpha cosine alpha. Okay, let's have a look. If the angle by which we rotate the coordinate system is 0, we expect that we get exactly the same moment, right? So in that case, we would have sine alpha, sine 0 is 0, so this guy would be gone. And we had cosine 0, which is 1, so we got I squared minus j squared, which is what we want to see. Okay? So yes, so this part here is a part that we expect to see here, but then in addition we have something that's ij, and ij is something that we know from a different moment. It's a kernel of a different moment, namely m110. Yeah, so in this moment we have ij I comma j comma k starting from -1 to 1, ij fij k. So which means there appears to be a relationship to a different moment. Yeah. And this happens. Okay, well let's put it this way. So when we rotate this by a specific angle. So when will cosine 2 alpha be 0? Let me think. So cosine is 1 at 0, -1 at pi. So it is 0 at pi half, right? So then it will be, so then when alpha is pi is a pi divided by 4, this here will completely disappear, and what we are left with is actually this kernel ij, which means that the moment m2 0 0 minus m0 to 0, this maps on m110 by rotation of alpha equal to pi quarter. Yeah, so these guys have this relationship. By the way, the lattice does not rotate by pi quarter. If we look at the lattice and we look at the projection in the set plane. So this will map only after a rotation by n times pi half. So let me see whether I can actually manage to draw this. So say, oops. So say this is our original plane. So we rotate this by pi half, which is by this amount. You can easily see that the lattice will return to itself again. When instead, if I've not chosen a good size here. Let me see. So suppose you rotate only by pi quarter. So pi quarter means you're not rotating by this amount, but you're rotating by this amount here. So then the thing you are mapping to, and this is now the lattice you are mapping to, will look like this. So they are, you see, not the same. So we'll get an exact match here, but no match here. Meaning that if alpha is not equal to n times pi half, would say that numerically, I mean, due to the discretization, this is what I mean, M110 and this M200 minus M020, they would be in different sets. And there are, in fact, lattice Boltzmann methods where we choose to have them with different relaxation rates. In particular, if we also combine this with a speed of sound that is not the standard speed of sound. Okay. Are you following me? Yes, okay. Then let's do the same thing. So this was only preparation. Let's go to the ghosts. What is about the ghost moments? Here we have, for example, the moment M210 minus M012, yeah, which looks like this: ijk equal to -1 to 1, I square minus j square. Oh, sorry, not j square. K square times j. Yeah. So this is how into Fijk. This is how we compute this moment. Yeah. So again, so there's something very similar to what we just had, and so we could say we'll rotate this guy. We do the rotation about the y-axis to this. So we'll have I y square minus ky square times jy. And I'm now not doing the computations. If you are interested in, yeah, do do the multiplication yourself. Here, this is the result. Hopefully it's correct. So what we get out of this is cosine 2 alpha. So the thing itself by cosine 2 alpha. Very obviously is alpha is 0, so this gives the original. So we rotate by 0 degrees. And here we have, in addition to this, 4 ijk cosine alpha sine alpha. So you see, this guy maps on itself, but it also maps on the moment M111, obviously, because in the moment M111 we have the kernel ijk. However, very important, it's no rotation. No rotation maps M210 minus M012 onto the sum. Okay? So there is no value for alpha that we can add here, and also no other rotations in other directions that will cause the minus here to disappear and to become a plus, right? So these two things, M20, M210 minus M01 and M210 plus M01, they are two different things, two physically different things, and so there are two different relaxation rates associated with them. Yeah, I mean, you can give them the same rate as if you wish, but in principle they are not coupled. Yeah, so even though they come from the moment M21 and M012, they are just permutations of the same thing. They end up in giving you two different distinguished physical things, and so they have different relaxation rates. Or we can give them different relaxation rates. So, however, as we've just seen, is that M210, no, M minus, sorry, minus M012, yeah, through a rotation by alpha equals to quarter of pi, gives us the moment M111. So from this, you should recognize that these two things are physically the same quantity. I mean, just in a different direction. So because the behavior of your system should not depend on how you place your coordinate system. Physically, these two moments need to have the same relaxation rate. They have to behave in the same way. Yeah? Do you agree? So I'm on the record. Tomorrow is the day when tomorrow, 18 years ago, I defended my PhD thesis. And this exactly is one thing that is written in my PhD thesis. And later I found that this is not the case, and it is not the case. I mean, let's put it this way. Physically, they need to have the same. They need to have the same relaxation rates. Otherwise, the system would be anisotropic. Well, the problem is that because we have missing third-order moments, the third-order moments are anisotropic to begin with, and in fact, there are ways to combine two different anisotropies to eliminate the anisotropy from the differential equation that you want to solve. yeah, but this is, let's say, next level. Yeah, physically thinking, you should say they should have the same relaxation rates, just because there are anisotropies in the models in itself on the level of the third order moments. Yeah, there is a possibility that you can combine anisotropies to cancel this out. And for this reason, okay, say it is, I briefly have to recharge my stylus. So they are in different groups only due to the anisotropy of the lattice. Only okay, if you could not follow this, this is next level. Not so important thing is we have three different. We have the sum of them. This comes in three permutations. And we give this the rate omega 3 plus. Then we have the difference, three permutations. Call this omega 3 minus. Oops, what I'm doing. Minus. And then we have this one guy, which we give the relaxation rate omega 111. Yeah, okay. I write this explanation here down. So the relaxation, so relaxing M210 minus M012 differently from M111 is anisotropic in an anisotropic no, is anisotropic in an isotropic, yeah, right, so is anisotropic in an isotropic distribution, but our so this would mean if we had no discretization of the velocity space, but the complete velocity space. But here, the lattice is itself anisotropic. So we get two anisotropies can cancel each other. Okay, so with this fact, it was possible, yeah. So we'll not talk about this here, at least not today. But with this, it was possible to eliminate this anisotropy, yeah, by choosing different relaxation rates and improve the method a lot, yeah. But this is, as I said, higher level. So then we have forced moments. Here we have again a sum of guys M220 plus M202 plus M022 equal to, and this is the minus 1. So this is ij squared, I square j square plus I square k square plus j square k square fij k. Yeah, so you have to go through all of these things for arbitrary rotations. This will always be the same. So we have I r square j r square plus I r square k r square plus j r square k r square is always the same as I square I square j square plus I square k square plus j square k square. So, and then this is isotropic moment. And then we have M210 minus M202, which again we can rotate about, say, this doesn't make sense, sorry, because this is a third guy. Okay, always watch what I'm when I write something stupid, yeah. M220 rotation. Rotation about the x-axis. So this gives us ix square j x square minus k x square is, if you do the math, I square j square minus k square cosine 2 alpha, if this is alpha is 0, no rotation, plus 2 I square j k sine 2 alpha. So what you see is this is the kernel for the moment, for the other moment, for the other countable moment. So this maps through rotation by alpha equal to pi quarter to M211. So here again, these things are physically the same thing, just on the lattice they may be considered different. So this is why we say we allow a different rate between them. So we'll have this one, we'll give this omega, we call the relaxation rate for this omega 4 plus. Then we have M220 minus M202 with 3 permutations. We call this omega 4 minus, and then we have M211, again with 3 permutations. And this we'll call omega 211. Yeah. So, and then we also have the higher ghosts. The higher ghosts, sounds crazy. Higher ghosts. So what is left? M221 with 3 permutations. Omega M221, and then there is only one in 1 of 6th order. This will give omega 2, 2. So, well, crazy stuff, isn't it? Yeah? Has anybody fallen asleep? Okay, then you won't answer. I just wanted to type you no once, yeah? Okay. Which means this thing comes with 10 different relaxation rates. Oh my God, we have to fix 10 different rates. Now, okay, now we've determined how many there are in principle, and now we come back to our favorite topic, the orthogonality. Orthogonality of the moments. Because this is something that's very important in the original MRT method, where we cause a moment to be orthogonal, unweighted orthogonal. And I have to remind you, a moment m phi, say ijk from -1 to 1, with a kernel phi ijk into fijk, and the different moments, say m psi over ijk from -1 to 1, phi ijk into fijk. So orthogonality, also orthogonal, orthogonal, if we can take the sum over the product of these two kernels, if this is equal to 0, then they are unweighted orthogonal. Yeah, so this is classical MRT, unweighted orthogonal. Unweighted orthogonality. So, and we recognized last week that this matters only for one moment, namely M22. But then we saw that the unweighted orthogonality caused it to crash. Now the problem here is that we have many different moments and this implies that the problem is now much bigger in 3 dimensions. And there is not one problem, but there is problems, because we have different moments that we have to take care of. So there is actually a specifically designed example that highlights this problem. So the problem appears, of course, in any random simulation, but if we want to highlight this problem, we can run a very simple simulation, that is the double shear wave experiment. So this is a thing where we have an analytical solution to the Navier-Stokes equation. in a periodic box. The Navier-Stokes equation has very, very few analytical solutions that are not in a periodic box. So the box has the size L times delta X, so it's just one grid layer, it's basically pseudo two-dimensional, and then 1.5 times the length L. And the solution looks like this, so we'll specify Ux as being equal to 0, Uy as being U0, L0 divided by L times sine 2 pi x divided by L times cosine 4 pi 3L z, and this will decay with time given viscosity nu times t, and this in this 2 pi by L 2 pi by L square plus 3 pi by L square. So this L0 and this and U0 are values that make this scalable. Okay, and U set is 0. So the idea behind this, yeah, this is not a very physically interesting problem. The reason why we have this is, why we have it this way, is that we want to have a velocity field that has gradients in x and in z at the same time. Yeah, so this is the idea behind this double shear wave thing. So what you do in order to test this is you init it, then you run it, then you measure the decay. So you measure the amplitude, and then you fit the measured amplitude to mu numeric. Right? So there is a specific, so this will decay, it's supposed, physically it's supposed to decay with this exponent, yeah? Now, there will of course be an error, and we can determine this error by measuring how it decays and compare it to the expected decay. And this error that we call the error in viscosity will be then the expected viscosity, the measured viscosity, so how quickly the wave decays divided by the expected viscosity. So, and then you do this with different resolutions in diffusive scaling. What we do is we get all ghost moments omega ghost is equal to 1. Also, we set omega p also equal to 1. And then we look at the results. And the results are also in my paper, but we now see them here. Okay, so there are different cases which I have not yet all explained. We'll have the classical MRT is in this. Then there is, of course, BGK. And then there is raw moments. Raw moments means this is the case where where it's a non-orthogonal MRT. Yeah. So, And here this is for different viscosity. So the upper part here is for relatively high viscosity, nu equal to 10 by the power of minus 2. And this is the case where we observe up here, so BGK, by the way, BGK has an order of magnitude smaller error than MRT. Take this, Li Shi. Yeah? So, the thing is, up here, this we are not talking about the cascaded and the cumulant here, but we talk about the MRT here. So we get this line for the MRT at this relatively high viscosity. If we go to lower viscosities, there is no MRT anymore because MRT, so the orthogonal MRT is unstable. Yeah, and it is unstable even if all the ghost moments are the same. You remember this was the problem last time, but here they are the same and it is still unstable. Then Ra moments, what is called here, so this is non-orthogonal MRT has large errors. There is something called cumulants, which we have not yet introduced, which has small errors. And the idea behind cumulants is a little bit more complicated than this, but the basic idea behind cumulants is that instead of having this unweighted orthogonality, we have a weighted orthogonality. But this is not all of it. We also have not Ra moments, but central moments. What is here called means cascaded lattice Boltzmann, and cascaded lattice Boltzmann is using central moments. But non-orthogonal central moments and non-orthogonal central moments are stable, but they potentially give large errors. So, do we want to understand why MRT breaks down? For this, we have to go back to our asymptotic analysis again. So I told you lecture 6 is pretty central to all of these lectures. So this we have to do to second order, and we look at the moment M, the general moment MABC now in 3 dimensions gives us MABC equilibrium. So we want to do this to second order, or all of this is second order, minus, say we have an associated relaxation rate, omega ABC minus 1/2, and here comes dxm to which order? Give me an order. One, yeah. So which moment do we have? What is that? What are the indices for this first one? Okay, A plus 1 and the others as before, right? BC, dym. So again, first order, A here B plus 1, C plus dy, dz, sorry, M, first order, A, B, C plus 1. So this is what happens here, and now we can generate an equation by a partial differential equation by saying that by choosing A equal to 2, B equal to 1, and C equal to 1. So this gives us the equation for this first order. So what the problem that we have in this model is the first order moment. The first order moment M211. This is the problematic guy. And by the way, now in between, in the beginning of this lecture, I told you that in this paper from 2002, where they introduced MRT, they did this only for the D3Q15 and the D3Q19. And in the D3Q9, in these models, you don't have this moment independently. So you don't run into this problem because you don't have the moment. Yeah. But on a completer lattice, we will have this moment. Okay. Completer is of course not a correct word, but bigger lattice. So we'll enter the numbers. We get 1 omega 211 minus this one dxm. So now we get 311 to first order plus dy m221 to first order dz m2. Okay, did I make any mistakes? No, don't. Okay, now we have to specify all these terms in here, starting with the equilibrium M211. Equilibrium to second order gives us, so we remember this can be done by factorization in the different dimensions. So we'll have M200 to zero order times M010 to first order. So this because this is a the M200 is an even moment. Yeah, so it has only even orders. It has only even orders. So then this means, because we do it to second order, if this is second order, then the other two both of them have to be zero order. And if they are zero order, and the velocity to zero order is zero. Yeah. So but this guy M200 of course has a zero order part. What is the zero order part of M200? What is the zero order part, the M200 to zeroth order? No. Yeah, but ux squared to zero order is 0. So there is something of zero order in this. I mean, it's related to the pressure, right? Okay, somebody else. I mean, you are right, there is ux square in it, but this is not all in it.
There's not the speed of sound square?
There's the speed of sound, right? So the speed of sound would be, this is the speed of sound squared, so this is theta times rho, right? So this is in it, yeah? So this is this because the speed of sound is not dependent on is of zero order. Okay, so I have another question. We have to normalize this by m 0, 2 zeros order. How many times? Is this already correct? This is how we wrote it in, yeah? By, okay,
I
by
would have said three
square,
times.
square, yeah? So, and as you said, so the speed of sound square is theta times uy, yes, uy first order and you set to first order times rho to the to zeroth order. So this is the equilibrium of this moment. Oh my God, we spent too much time on this. Then we have M311 to first order, which is an alien, and it's an alien of one, as an alias of 111 to first order, and to first order is because this is ux, uy, and uz times uz, yeah? This all together would be third order, so the first order of this is 0. And then we have the other guys here, M212 to first order is theta square rho 0 uy first order, and M221 first order is theta square. I miswrote this again, sorry. M221 is theta square rho 0 uz first order. So then we can plug this in the above equation and get M211 to second order is equal to theta rho 0 order uy first order uz first order minus 1 over omega 211 minus 1 half theta square rho 0, and here we get dy uz first order plus dz uy first order. Okay, so what do I want to torture you here? Why am I torturing you with all of this? Actually, this is something that the Lattice Boltzmann community required a lot of time to figure this out. And it's, you come to the right place if you want to know the details here. Yeah. Okay, I got 10.1. I was missing what you wanted to say. Did I make a mistake? Equation number. Because we are in the 10th lecture. Okay, yes, thank you. Okay, 10.1, thank you. Yeah, I missed. Okay, I thought we were in the 9th lecture. No, we are in the 10th lecture, yes. I think it will be wrong okay, it doesn't matter. Okay, the hydrodynamic, we compare this to the hydrodynamic moment that we get when we set A equal to 0 and B equal to 1 and C equal to 1, because then we get this guy, M011 to the second order is rho, so this works the same way as the other one. You set, so this is its equilibrium, minus, here we get omega bgk, because it's hydrodynamic. And here we have now theta without square. But the thing is, we have the same derivatives here. Same derivatives. dz uy first order. Right. So now we can solve this for this guy back here and say that theta rho 0 dy set first order plus dz uy first order is equal to minus m011 plus rho 0 uy first order uz first order divided by 1 over omega bgk minus 1/2. Okay. You guys, are you still awake? Then think about this. This equation 10.1 contains these derivatives here. So now we can plug this part here into this equation here. And from this, we determine the relationship between these moments. M211 to second order is equal to theta rho 0 uy first order uz first order minus now 1 over omega 122 minus 1/2 divided by 1 over omega bgk minus 1/2 theta, and here comes minus m011 to second order plus rho 0 uy first order uz first order. Okay. Now I know it's crazy way we came here, and now you're pretty. Why am I torturing you? So this is a very important thing that you need to see. There is a relationship. So there's now, okay, there are some velocities in here, but there is no derivatives in here. Yeah, the derivatives are somehow in these moments. And what you see here is that there is a relationship between this hydrodynamic moment, which is what it is because it's a physical quantity, so there's nothing under our control as is omega bgk. We have this relationship between this moment and this ghost moment here, the ghost moment that we want to disappear. Now this moment, so this relationship involves that we divide by 1 over omega minus 1/2. What is this here? What is the physical meaning of this here? 1 over omega minus 1/2. It's the viscosity. You see, we divide by viscosity. Viscosity is supposed to be small. Yeah, so you want to simulate turbulent flow, then this here is extremely small. You divide by something that is extremely small. So that means if this guy is not 0, then this ghost will be extremely large. So it has extremely large influence because it is large. Yeah. We assume there's asymptotic. Yeah, you know, it comes later. It has a different asymptotic. Yeah, so it doesn't show up in the leading order equation. But you have to remember it's numerically very large, and so it will show up in your actual simulation. Okay. Let's write this down. So in BGK, we don't have a big problem because in BGK, these two guys are the same. So, okay, sorry, I have to recharge. So why does BGK work? The BGK works because these guys are the same. So then you would divide something very small by something very small, which again is 1, right? So then it's not such a big problem. But in MRT, omega BGK is going to 2. And if you want to eliminate your ghosts, so if you want to be clever and say your ghost, okay, we'll want to get rid of them, we set them to 1. Yeah? So then you have something that is not small and you divide it by something that's small. So this is a ghost, but it's a big ghost. Yeah, because 1 over omega 2, 1, 1 minus 1/2, which together would be 1/2, is divided by something that is basically going to 0. This will go to infinity. Yeah. Okay. Which means for an unweighted orthogonal MRT moments, so say we define this guy here, N211. So this is defined like this: so 3 times M211 minus 2 M01. So if we plug everything in here, take this to second order, we'll end up with 3 times M211 equilibrium to second order minus 2 M011. This is a 1 equilibrium to second order minus 1 over the omega ghost modes minus 1/2 rho theta rho 0 order to 3 times theta square minus 2 theta into dy u z first order plus dz uy first order and closing brackets. So if we introduce all of this, we get 3M211 equilibrium 2 minus 2M011 equilibrium first order. And here we again have 1 over omega g minus 1/2 divided by 1 over omega bgk minus 1/2 3 theta minus 2, which is non-zero, yeah, times M011 to second order minus rho to 0 order u y first order times uz first order. Okay, so this is, now we have done 2 things, by the way. Just to remind you, the ghost, sorry for going back, but the ghost that we were talking on here is not for the usual MRT, but is for the unweighted MRT. Yeah, so unweighted MRT would give us this, and the weighted MRT would give us something similar, and maybe even worse because it crashed. So this is still large because we have the same problem. Yeah, we divide something that is non-zero, that is large by something that is small. The only thing that changed here is the sign in this relationship. And now let's come to this important question of, is there a better way? And this, you can imagine already, is by using, when unweighted, I mean, why do we call it unweighted? Because there is a weighted orthogonality, and this makes your life easier. Moment. So let's call this small n, n2, 1, 1, and this is defined as m1, 1, m2, 1, 1, and now if you think about this, so how do we make it weighted orthogonal? We take we think we weight it with the equilibrium, and the equilibrium, yeah, you remember, is basically the equilibrium of m200 times the equilibrium of m011 and m001. Yeah, so the equilibrium of m200 to the leading order, so the zero order is theta. So we just take theta and say this is theta minus theta m01. So next time we get this into more detail, but say this is now our weighted orthogonality. Yeah. Now writing the equation in terms of weighted orthogonality gives us, from the non-weighted, from the original raw countable moments, get this here, equilibrium to second order, minus 1 over omega g minus 1/2, and here we get theta square rho minus, and this is interesting, yeah, so by this arrangement we have theta square rho, and because we multiply m011 by theta, we get again theta square rho, all of this to zero order, into the derivative in y direction of z, first order, plus dz u y first order. So you notice this one, yeah? This here is zero. So this eliminates this relationship, and this moment here just doesn't depend on these derivatives. And now you could say this is a numerical fluke, yeah, because why do we care that this moment depends on it? Let's go back and write the countable moment. So let's say we are interested in what happens to the countable moment, provided that we relax the orthogonal moment. So we'll invert this. We write m211 is m211 now plus theta m011, to second order, and this gives us M211 equilibrium to second order plus theta 1 over omega bgk minus 1/2 theta rho 0 dy uz first order plus dz ux first order. And remember, this was a guide that when we use either no orthogonalization or we use orthogonalization in unweighted orthogonalization, this guy would be very, very big because we divide by viscosity. Now, we are no longer dividing by viscosity. Yeah? In fact, we're multiplying by viscosity instead of dividing by viscosity. So we make this guy, in fact, a small ghost. This is a small ghost. And therefore, it will not cause these problems. Okay, guys, I have a little bit of an exercise left. Have you any questions? And if you are able to follow me, it's not so difficult what we want to do today. Any questions before this? No questions. Okay, let's go. Let's go to our code. Yeah. So last time, I mean, we cannot code now for where's this? Where's our code? Yeah, here's the code that we have implemented the last 2 times. So in principle, to see what we learned today, there may be questions before. Oh, thank you. Wait, I'm going to solve this problem. Wait, I have to. Why do I? We see the code. Okay, so great. Okay, so this is the code that we have been implementing, and of course it's 2D. And the problem we were talking about today is of course 3D, but we were also talking about in the last few minutes about weighted or non-weighted orthogonality. And the one thing that we can still do with this code is to use this one moment that where orthogonality mattered, and instead of using either non-orthogonal or unweighted orthogonal, we made it weighted orthogonal. So I'll take the non-orthogonal example here, this function. I'll copy all of this and paste it. So, and then let's call this function instead run MRT W orthogonal, the weighted orthogonal. Okay? So the only moment I remind you in 2 dimensions that make it different is this M2 to M22, yeah? So, which in the right, so I've eliminated this, yeah? So you remember we had this epsilon. We used this epsilon for the weighted orthogonal. Now let's call this, because I call it, okay, I'll call it N22, yeah? And I want to make it weighted orthogonal. So we start with M22, and now I have to subtract, have to build a weighted format, and the weighted format is that I subtract the contribution that comes from the second moment. So what is the contribution of the second moment? Maybe we'll do this in Mathematica first. I don't know whether Mathematica works because I'm traveling. Activated. Okay, I've already done it here. So let's fake this. Oh my god. Doesn't matter. Okay. So what do we want to do? So we oriented in our, we have the moment M22, right? So the moment M22, okay, this is not a good, will not be very visible. M22. So the moment M22 has the equilibrium theta. So I'll just write 1/3 plus ux square times 1/3 plus uy square. So now we want to get rid of the part that is related to the other moment. For the other this second order, you still, oh, sorry, yeah. Okay, I have to do it in another way. Wait. You are so right. You know what I do? Okay, I share the entire screen, so this is apparently the only way I can do this. Okay. Yeah. Okay, sorry for this. Yeah, today is a bit, the setup is a bit complicated today. Okay, you hopefully agree that, okay, there's the row is still missing, maybe I write row. So this is the equilibrium, so far this is the equilibrium for the second order moment, for the first order moment, right? The equilibrium of the second order moments, the product of them. So now we want actually to make this independent of the second order moment. Yeah? And in particular of the sum of the second order moments. So the second order moments, they are here. So what is the sum of the second order moments in the equilibrium is 1/3 plus ux square plus 1/3 plus uy square. So now when we subtract this, okay, and maybe times rho, we wish to have this times rho. So these are these equilibria, right? So will they disappear? No, they won't. So so for example, ux, so we'll have here ux times 1/3, but here we'll have just ux, right? So in order to make them disappear, and this is similar to what we have had before, we have to multiply again by theta, which is we divide by 3. However, if we do this, we also don't get rid of everything, because we still have here 1/3 plus 1/3, and here we have 1/3 times 1/3. So we have to get rid of 1/3 times rho. And from this, okay, from this we get this, and if we expand this, if we expand this, we only get the first order part. Okay, so the first order part is this part. So there's no zero order part. Yeah, there's nothing with rho left, and there's nothing with ux square, just ux square or just uy square left. Yeah, so we just focus on this part here. So this here gives us a way of orthogonalizing the moment in a different fashion. And so what we see is we have here the moments. Yeah. Okay. Maybe this is a little bit mysterious, but this is what we are also studying in the next lecture. So try to remember what we did. We take M22 and then we have the sum M02. Yeah, so this was the first moment, M20, and all of this we wanted to divide by 3, but divide by 3 point dot. But in here we had to subtract 1/3 to also make it orthogonal to the zero order moment, which doesn't matter because the zero order moment is not relaxed, so this wouldn't make any difference. But say this is now our new weighted orthogonal first order moment. Then we have to introduce a new collision for this. N22 will now collide as being N22, plus we again use the same relaxation rate omega 4 times, and now you remember, or you see this here, this is rho times ux squared times uy squared. So let's just type this is rho x y times u x y. Okay, I'm going to copy this just times this times okay, I'll copy this 4 times and then I'll just change this to y and subtract minus n22. Okay, do you agree with this? You're following? No opinion? Okay. So you said yes when I asked no opinion. Okay, now we have to do the back transform of this. So for the back transform, what we do is we just solve this guy. Okay, let me take just this guy down here. Oh, yeah, you have a question. I mean, this is not the equation that I wrote. There is a minus 1/3. Okay, what is with the one that I wrote in Mathematica? So this here is M22, right? Or the equilibrium of M22. This here is M20. This here is M02. Yeah? And this is what we wrote. M22, then minus M20 plus M02. And then we also had minus 1/3, because this is this minus 1/3. So, wait. So you are questioning whether there is supposed to be a row. Yes, there's supposed to be a row. So, right, there is supposed to be a row. Row X, Y. Okay. So, further things. No, this does not come from the speed of sound squared. So this is so this comes actually from the speed of sound. Yeah, from, you know, because we have here two of them. We have here two of them. This is where it comes from. Okay, the details how we get to this is a kind of more what we'll intend to do in the next year. Yeah. So let's just take this guy. Thank you very much that you pointed out that there was this row missing, and do it the other way around. So we want to have after the collision M22 again given N22, and this we get by, you know, inverting this sign, obviously. Yeah. So and then we do the back transform and go on as always, and then we have to add this to our interface, the new function, of course. So, and I called this W and W. Okay, let's save this. And let's see whether I have the right demo. Yes. So, and then compile. So, slow computer. So there, okay, we still get this warnings. I have not figured out how to deal with this. Okay, we'll have to speed up because I have only 15% battery left. Okay, we have to. This is the Python that we had. We have to restart everything. Yeah, I remind you that. Oh, I already tested this. So what was our problem? We had MRT. So we wanted to run MRT. So some people disappear. Okay. MRT, you remember if the relaxation rate for rho is not the pressure moment is not the same as for the last one, it will crash as we see. Let's interrupt this. I remind you, we were using relatively low viscosity. We have an omega of 1.995. So let's first see whether we have our function actually working here, and W auto. So first of all, let's see whether it works in the first place. Let me see. Run all. Okay, so we have set all the ghosts and pressure relaxation rates to the same value. Yeah. Pretty low viscosity, and it seems to work. Okay. This seems to work. And let us remind that if we had a different value here and we use the usual MRT, yeah, so this was the problem with our usual MRT, it will crash. Now we could solve this problem with using non also. This would work. And let's see what happens if we have a weighted, if we instead we have a weighted orthogonality. Okay, test. Okay, weighted orthogonality, so we can use orthogonal moments. If we use weighted orthogonality instead of unweighted orthogonality. Now, I believe in this case we won't see a lot of difference with regards to the stability. At least this is what I believe with regard to stability to the non-orthogonal version. Can try something different. I don't know. Take a different rate in the fourth order moment. Let's run this again. Okay, it does not crash immediately. Let's somehow get rid of this. So I believe that there may not be a big difference in stability to the non-orthogonal version. Let's see this again. Okay, this also stays stable. I don't know when we take this. Okay, now this doesn't work. This let's see whether oh. Okay, now we see a difference here. Now we have a relatively high relaxation rate for the fourth order moment, yeah, and it still remains stable with the weighted orthogonality, yeah. Whereas we tested the same value for the non-orthogonal version, and this crashes immediately. I stop this. Okay, I have to restart my kernel. Are you still here, guys? Yes. Okay. Let's compare this again with MRT. So MRT obviously crashes, then MRT non-orthogonal how was this written? Non-ortho crashes. MRT weighted orthogonal runs. So again, we found an improvement. Should I try to run it with 1.9? If this doesn't run, then we are done for today. Okay, even with 1.9, yeah. So now we have the opportunity to really change this rate, yeah, without timed out, cancel. I don't know what this is. So now we have the opportunity to really change these relaxation rates without killing our simulation. Okay, so I guess then that's it for this year. We'll see each other again at, I believe, the 10th of January is the next. The 10th of January will be the next lecture in this theater. I will now stop all recordings and then you can ask remaining questions. You see.